In this video, we're going to take a closer look at how we can use Bode plots to investigate the stability and also quantify the stability of a system. And so as you can see by the title here, we're going to do that with something called phase and gain margins. And so we'll get to that in a little bit. But right now we want to note that our Bode plots are typically going to provide a simpler test or sort of a quicker test than looking at our Nyquist plots, which we discussed in the previous video. So the first thing I want to do is go back to sort of our basic definitions of stability and instability in terms of our loop gain, which was our T of j omega. So if a system is stable, we said that the loop gain magnitude is less than 1 when our phase is equal to negative 180 degrees, and our system is unstable if the loop gain magnitude is greater than or equal to 1 when our phase is negative 180 degrees. So sort of one little adjustment we want to make here, typically we know when we're talking about Bode plots, our magnitude is in dB, and so what that means is we're taking 20 times the log of whatever value. So in this case, if 1 is our key value for this magnitude, if we want to convert this to dB, so we can adjust this, and so we have this now in dB. So we say our T of j omega in dB is going to be less than 0. And our T of j omega in dB is greater than or equal to 0 at this key phase angle of negative 180 for stability and instability respectively. So let's come down here then and look at some plots. So I've plotted a frequency response for some arbitrary function. So in the top plot, you can see we have the magnitude of the loop gain, and in the bottom plot, we have the phase of the loop gain. Both are plotted with respect to frequency, and I've aligned these frequency scales such that, for instance, if we said we have some frequency of, I don't know, 100 here, then this would also be 100 here. So they're sort of meant to be aligned, that's why they're stacked vertically. So the first thing we want to do is let's determine if this system is stable or not. And then we're going to come back from that and we're going to say, well, how stable is this system? So we can see that because the phase is reaching this negative 180 degrees and in fact going beyond that, we have the possibility for instability. So if we look here at this key point where our phase is negative 180 degrees, that's where we're going to want to assess the value of our magnitude. So coming back up here, when our phase is 180, we want to check this magnitude value to see if in decibels it's less than 0 or greater than or equal to 0. So let's come down here and do that. So let me get rid of this and let's put some dashed lines here. Okay, so we say because these frequency scales are the same, I'm going to put a dashed line going up from this point where we said it's equal to negative 180, and we're going to check the value of our gain. And so in this case, we see that it is the magnitude of our loop gain in decibels is less than 0. So that means that our system is going to be stable. And so here, of course, we see at this point it's less than 0, so that's how we can determine it's stable. So now let's say we want to quantify the degree of stability. So it's not enough to just say, yes, the system is stable. We want to say, how stable is it? Is it stable to where if something changes slightly, it's going to become unstable? Or does it have sort of a bigger safety margin where it can change a little bit and remain stable? So there are two terms, as you saw in the title, that we're going to use to do this. So we have some additional terms we're introducing, which are going to describe our degree of stability. Or in other words, to quantify how stable a system is, how much it can change and remain stable. The first of these terms is our phase margin. And so I'm going to define it down here first, and then we're going to go back up to the plots and see what that looks like in terms of the plots. And so what our phase margin is this is just the difference between our phase angle so our phase, got an extra letter there, difference between our phase angle where that magnitude is equal to 0 dB and where the phase angle is equal to negative 180. So something like this. Okay, so that's maybe kind of hard to understand just in words, so let's come back up to our plots. So the difference between where our phase angle is 0, where the phase angle corresponding to this magnitude in dB being 0, so let's determine where that is. Well, up here we look at our magnitude plot and we see that that happens in this highlighted area here. So let's go ahead and put another dashed line, because again these frequency scales are the same, so let's put a dashed line going down from this point to our phase plot. So starting here, let's put a dashed line here, straighten that out. And so basically what we see here then is we're going to be comparing between this frequency point, which is the frequency that corresponds to the magnitude in dB equaling 0, and our frequency where our phase is negative 180. So let's come in here then, and we can define, or we can kind of label this a little more clearly. So at this point, and this point is where we're sort of going between, and we say that the distance between these two then is our phase margin. So of course, if we wanted to know the actual value, we would just extrapolate this back over here and we could figure out what that angle is, and then the difference between these two is going to be our phase margin. So typical good values of this are going to be 45 to 60 degrees. Typically 45 to 60 degrees are sort of desired values, because again, that's going to give you sort of a safety margin in terms of you can adjust your system a little bit and still remain stable. So the other metric we have is our gain margin. And so what our gain margin is just the magnitude in dB at the frequency where our phase is equal to negative 180 degrees. And the reason we're not having to do a difference the way we did up here is because, of course, our sort of key value that we're checking for our magnitude is 0, so it's just some value different from 0 is going to be that value. So again, this is going to make more sense in the plot, so let's come back up here to our plot, and we're looking at the magnitude in dB where our phase is equal to negative 180 degrees. And we've actually already drawn that line here, so the rightmost purple dashed line is corresponding to where our phase is negative 180 degrees. And so if we come up here, we can see it corresponds to a gain, magnitude in dB where I've highlighted there. So what we can do is we can define this as well. So we say we're comparing this, of course, inherently to 0. So comparing between these 2 points gives us our gain margin. And so again, we could take this over to our axes over here if we wanted to figure out the exact value in dB for this gain margin. So it's worth noting that both of these values are typically reported as positive, so both the gain and phase margin are positive values. Of course, we can see, for instance, that any value here would be negative, so maybe this was a negative 10 dB, but if you were to report this value as a gain margin, you would say you have a gain margin of 10. And keep in mind, as I've been saying, that these gain margin and phase margin, it's sort of 2 ways to represent the same thing. And having a sort of larger margin, whether it be gain or phase, indicates that you have sort of more room to adjust your T of j omega, your loop gain. Why would that be being adjusted? Maybe you have temperature effects which are causing changes. So you're not worried about those changes leading to the system being unstable. So what we're going to do in the next video is come back and look at an example of how we can design for a particular phase margin. And then in subsequent videos, we're actually going to look at how we can compensate the system to get a particular degree of stability.